Let's dive right into this explainer and explore how everyday magic, like your phone's autocorrect, actually works under the hood. It all relies on this fascinating piece of computer science that dictates how machines understand the differences between words. We're talking about the Levenshtein distance. And computing this? Well, it reveals a massive divide in how we solve problems. On one side, you've got the chaotic, endless branching of plain recursion, and on the other, the highly structured, super efficient grid of dynamic programming. So let's just see how this plays out, right? We're going to look at time complexity, the true nature of exponential growth, and how changing the very architecture of a solution can turn a literally impossible task into an instantaneous one. Okay, so let's establish our baseline here. Take two slightly different words, transformation and transportation. They're both exactly 20 characters long. Now, when spell check evaluates these, it computes that Levenshtein distance, which is just the minimum number of insertions, deletions, or substitutions needed to turn one word into the other. And the most straightforward mathematical way to do this is with plain recursion, basically breaking the problem down and checking every single possible path of edits, step by step. Sounds totally intuitive, right? You just traverse down a decision tree, comparing characters, and branching out every time there's a mismatch to see if a deletion, an insertion, or a swap gives you the best path. But to really understand what plain recursion demands of a system, let's set the stage with some serious computing power. Imagine a CPU executing a billion operations a second. A billion! You'd naturally assume that comparing two 20-character words would be an absolute breeze for hardware like that. I mean, come on, it's just a few letters. But when we apply that plain recursive algorithm, our incredibly fast CPU immediately smacks into a computational wall that honestly defies human comprehension. The sheer volume of recursive calls branches out so aggressively that the processor just gets utterly bogged down traversing all these redundant pathways. Let's scale it up just a tiny bit. Let's go from 20 characters to just two 50-character sentences. Think about that for a second. That's just a standard email subject line. The operations required for plain recursion approach 10 to the 80th power. Let that sink in. 10 to the 80th. That is roughly the estimated number of atoms in the observable universe. And that's just for two short sentences. Our blazing fast CPU is entirely, completely meaningless against a number that massive. The math simply crushes the machine. All the processing power in the world cannot save an algorithm with time complexity this punishing. And this leads us to the ultimate computational showdown. Just look at how this scales. As string lengths go from 10 to 20 to 30 characters, plain recursion balloons from taking 3 seconds to 380 years to literally multiple ages of the universe. Now compare that to dynamic programming, or DP. Instead of endless branching, DP uses a matrix of cells to store states, a technique we call tabulation. For length 10, it's instant. Length 30, instant. Even scaling way up to comparing massive strings of 10,000 characters, DP processes the matrix in about 1 single second using 100 million cells. It's a breathtaking difference, isn't it? The problem transforms from navigating this infinite, impossible labyrinth into simply filling out a grid. The math behind this creates a totally violent performance gap. Dynamic programming scales at roughly m times n. That's the length of the first word multiplied by the length of the second. So it operates in polynomial time, specifically quadratic if the strings are the same length. Plain recursion, on the other hand, scales at roughly 9 to the power of n. These two formulas don't just give you different results, they honestly belong on entirely different kinds of charts. One is this manageable, predictable slope, and the other, it's a vertical rocket launch straight into infinity. To really grasp why this gap is so violent, you've got to look at the compounding effects. Calculating the famous Fibonacci sequence with recursion is notoriously bad, right? That scales at 2 to the power of n. But Levenshtein distance branching is roughly 3 to the power of m plus n, which simplifies to about 9 to the power of m. Notice that both the base and the exponent increase. So you aren't just paying twice as much for every character you add. You are paying exponentially more. It's a compounding nightmare that guarantees a total system failure on even the absolute most trivial text comparisons. So we have to make a crucial mental flip here. When we look at these astronomical savings, literally going from the lifespan of the universe down to a single millisecond, we have to ask, is dynamic programming just a neat trick to speed things up? Is it merely, optimizing the code to run a little leaner? Because it's incredibly tempting to view algorithms this way, just as clever little tools developers use to make things a bit faster or save a tiny fraction of a second of battery life. But the answer is a resounding no. And the absolute reality of modern computation is this: dynamic programming doesn't make Levenshtein faster. DP is what makes Levenshtein exist as a computation. Without it, comparing strings programmatically is purely theoretical.
It belongs in the realm of mathematical philosophy, not functional software. Because let's face it, the universe would literally end before your computer finished checking a simple paragraph for typos.
So how does it actually pull this off? Well, the secret lies in overlapping subproblems. Comparing those two words we looked at earlier really only requires solving a few hundred unique combinations. Plain recursion blindly walks through those 9 to the power of n paths, computing the exact same string comparisons over and over and over again. But dynamic programming, using memoization or tabulation, just flat out refuses to do redundant work. It calculates a subproblem once, caches the answer in a cell, and just looks it up in memory the next time it's needed. It is the ultimate form of working smarter, not harder.
And this strict refusal to do extra work is exactly what powers the tech in your pocket and in cutting-edge labs right now. Every single time your spell check highlights a typo, every time a software engineer uses a Git diff to compare thousands of lines of code, and every time biologists use DNA sequence alignment tools to compare ridiculously complex genetic strings, they are relying on dynamic programming to measure edit distance. The underlying architecture of all these tools maps perfectly back to that simple grid of cached solutions. It's just amazing to realize that without this specific mathematical paradigm, so many of our modern conveniences would fundamentally cease to exist. Think about typing on a smooth glass smartphone screen without autocorrect fixing your clumsy thumbs in real time. It wouldn't be a feature you wait 10 seconds for. It's a feature that, mathematically speaking, could never have been programmed onto the device in the first place. The hardware simply cannot brute force its way past the math. No way.
So the main takeaway here is that the harder a problem's branching becomes, the more dynamic programming stops being optional. It acts as the absolute gatekeeper to computation. I'll leave you with this provocative thought. Look at your own workflow. At what point in your complex problem solving does finding a shortcut stop being a luxury and start being the only way forward? Where might you be doing the equivalent of plain recursion, just redoing the exact same work endlessly, when you could just be saving the answer? Thanks for joining me on this explainer, and keep looking for those smarter paths.